So good afternoon, everyone again. And on this part, basically chapter 6, we showed example of seismic retrofit in this guideline. And 6.1 basically discussed about the moment resisting frame, and 6.2 discussed about the flat plate structure already discussed by Mr. Samdani earlier. So I will briefly discuss on this chapter. So this is the building that was selected for the analysis in this guideline. Basically, this is an existing 6-story Bangladeshi building. And as you can see or recognize, it's a typical looking residential building in Bangladesh, where it's symmetrical along with this vertical line. And this is the column schedule of that building. It has only 3 types of columns, C1, C2, and C3. And these are the layout as such, which modified going to the upper floors. And we converted this drawing to SI unit. And this is our converted drawing for the calculations. And as you can see, the 3 types of columns are actually basically square rectangular columns in the corners, and 2 types of rectangular corners in the middle, like defined dimensions. And 8 to D6 are basically like our denotation for simplicity of calculation process. And these are the grade lines as such. So the basic information of the building is a 6-story Bangladeshi building, moment resisting type. Foundation is pile foundation. Building's construction year is 2002, and it was constructed by Public Works Department under the government of Bangladesh. And its location is in Dhaka city. And material properties for this building was 25 MPa for concrete strength and 450 MPa for river strength, and also deformed river were used for this building. This is the overall evaluation flow. And overall, I would like to say the overall flow, not the evaluation flow, because this also includes the retrofitting part. So at the start, we determine the seismic demand index IS0 as discussed earlier by many other presenters. This is according to CNCRP guidelines, or which is actually based on the BNBC recommendations or BNBC guidelines IS0, also discussed by Rafiqul San earlier. And we will determine the seismic structural performance according to SATREPS-TSUIB evaluation guideline, which was presented in a seminar last April, and also existing PWD guidelines such as CNCRP or BSPP guidelines. So those parts are already covered. So in this guideline, we will, or in this presentation, I will not discuss about this part, and I will skip over the evaluation process of that part. And then, according to this SATREPS-TSUIB guidelines, a judgment for joint failure, such as those kind of poor joint failure, is judged, and their capacity and demand is determined. If the capacity is higher, then we don't need to do retrofitting. If the capacity is lower, then we need to consider one of the cases. First, the original deformation limit. Was it actually exceeding the limit of F limit, which is 2.2? If no, then we can consider any of the existing retrofitting method or new method proposed by current guidelines and previous PWD guidelines. If the capacity expected is over the F limit 2.2, then we need to provide retrofitting to the joint to improve the structural integrity, as discussed in section 3.1, that when going over the deformation limit of 2.2, there lies a possibility of pullout in some of the exterior beam column joints. So in that case, if we want to have a structure with a capacity higher than that, we need to consider retrofitting for the joint to improve the structural integrity. And then we just basically perform similar small judgment if the capacity is greater than demand or not. If not, then we might need to demolish or come up with some other idea. Right now, that's based on the engineer's judgment. So the green part is basically SATREPS-TSUIB, this project's first guideline, which is the evaluation guideline. And the blue part is this guideline, SATREPS-TSUIB seismic retrofit guideline, the current one. So how to determine the seismic demand index? It's found by this equation, as briefly introduced by Rafiqul San. And for this particular building, we didn't have the soil type data. So we considered the worst condition for Dhaka city, which is SD type. If some information is not available to engineers while calculating, they should assume conservative estimations or assume something that will give conservative estimations. As Nakano-sensei a little bit earlier mentioned, conservative estimations is really good for us. So in that case, we considered the worst type, and that gave us a IS0 or the seismic demand limit of 0.36. What that means, I will come to this point later. And for determining each member strength, the primary load-bearing members such as column or other cases, other parts, we used SATREPS-TSUIB evaluation guideline and also existing PWD guidelines, all of them combined together, and we determined the member strength, strength index C, and ductility index F. And these parts were actually discussed on the previous seminar, so I'm just skipping over that calculation part. And I'm just showing the output of that part. After doing that calculation, you will find this kind of relationship between C and F, where C is the strength index indicating in the Y direction, and F is the ductility index or deformation index representing the X direction. So for this particular building, it has two directions, as you know. This is the X direction and this will be the Y direction for this particular building. And the performance of each floor will also change because of the actual load and the load sustained by each story. So the capacity is found something like this based on the C and F relationship. And also a little bit earlier, I showed that the demand for this particular building in Dhaka city was 0.36, but that is represented by this red curve. So if any particular story in any particular direction is above this demand curve, then we can assume that story in that direction to be safe. If not, then we need to provide some strengthening or retrofitting for that particular story in that particular direction. So as you can see, there are many points over the different demand curve. So how to determine the performance? So to determine the performance point, we have to take each of the peaks and then determine the maximum, which peak gives the maximum performance. Let's take an example of second floor in Y direction given by this green line. It has 5 peaks, 1, 2, 3, 4, and finally this is the 5th one. So for this case, we determine the story modification factor by this equation where n is the number of story and I is the story concerned, in this case 2 and 6. And strength index is basically summation of all the load-bearing members, strength index C, and then at that point, and then the corresponding ductility index for that peak. If you multiply these three together, you can get a basic seismic index E0. The maximum of the E0 value is taken as the performance point of that particular level. So in this case, peak 2 has the maximum E0 value. So peak 2 will be the performance point for that floor in that direction. Applying this to all the stories in all the directions, we can determine the performance point of the building in each floor in each direction. And we determine which cases are over the demand curve and which cases are below the demand curve. So if something is below the demand curve, we need retrofitting. But before moving onwards, as we can see, let's go to the next step. Next step is basically according to this guidelines, previous manual, evaluation manual, which states that if the building was constructed between 1995 to 2006 or later, and deformed bar were used in the construction, then there exists a possibility. You cannot know that, but there exists a possibility that the exterior beam column joints might fail by pull-out failure and exhibit some catastrophic loss of the building. So if those criteria are satisfied according to this guideline, we will perform a defined kind of pathing, which is basically limiting the deformation capacity to a point where pull-out failure will not govern. Other types of failure will govern before the initiation of pull-out failure. So from our limited experimental test, we found that the pull-out failure initiates in the exterior beam column joint at a deformation index or deformation limit of 2.2. So if we limit the performance of the structure within this 2.2 limit, then we can say that pull-out failure will not occur, or the building will not deform that much enough that pull-out failure can initiate. So that's what we are doing. Because this building was constructed between that time frame, 1996 to 2005, and deformed bar was used. So we are just going to as a penalty, we are just going to reduce the capacity of this building. So how do we do that? Story modification factor stays the same, strength index stays the same, but the deformation limit, we only allow the building to go up to the point where pull-out failure will initiate. That's 2.2. So anything over that is penalized and brought to 2.2, and that's how we can determine the performance point here. Again, it stayed same at 0.2, and that was applied for all of them in both direction X and Y for all the floors. And this is the summarized table of that. So for each stories, now the modification factors are different because the story changes. And there's actually two equations to determine this basic seismic index according to PWD manuals, as explained by equation 4 and 5. And as explained in the guidelines, you take the maximum value of either of the equation and determine that as the basic seismic index, E0. So for our case, in this particular building, everything was governed by equation 5, and that's the values in both direction, X direction and Y direction as shown here. And the corresponding ductility of each floor was also shown here as can be seen. So the performance of the building is actually modified something like this. I showed earlier that you can go up to 3.2, which is the maximum limit considered under the PWD guidelines. But since the building had some certain criteria that it ticked off, we are penalizing the building in a saying that there exists a probability of pull-out failure if we consider any performance of the building in these parts. So we are simply ignoring that capacity, which is there, might be there, but there might also come with a penalty of such kind of pull-out failure in some of the joints. So in this case, now we will judge if the demand capacity is actually satisfied, if the capacity of the building is satisfied the demand. If you see closely, then there is actually one floor in one direction. This is first floor, and in X direction given by the shown in this particular figure, that is actually below the demand curve. So this is actually not safe. Other floors are actually over the demand curve, so they are safe even after considering that penalized limit. And similar for Y direction. For Y direction, actually everything is slightly over the demand curve. The first floor just marginally going up, and other floors have some safety margin. And seismic capacity index, I just said about the capacity. How do you determine that? This is also actually explained in the previous manual, evaluation manual, IS, by IS, and also discussed by other presenters earlier. It's a summation of multiplication of E0, basic seismic index, ST, irregularity index, and T time index. For this particular building, these two turned out to be 1 and 1. So IS became equal to E0 as calculated in the earlier table. So for each floor, the demand is same, 3.6 for this particular soil type, a particular acceleration in Dhaka, and that's probably the worst case for Dhaka city. And the demand seismic capacity of each floor in each direction are found such that 0.311 for X direction, first floor, and others were above. So we come to a judgment if the seismic performance is okay or not good. So for this case, as already explained, second to sixth floor, everything was okay. First floor, only one direction, not good. So we need to do some retrofitting or some strengthening to this particular floor to declare this or mark this building as safe. So what kind of retrofit should we do? The seismic capacity of the first floor obtained at a ductility of 1.59 here, 1.59, which is considering the structural performance penalty of 2.2. That means that this building is expected to fail in some other mode at a deformation limit of 1.59. And as found experimentally earlier, that pullout occurs at a point of ductility limit of 2.2 or higher. So which means that this particular floor will never get to that deformation limit where pullout can initiate. Even though it might have the worst condition as the anchorage, it will fail in other failure modes before that can initiate. So retrofitting for strengthening the joint in this case is not ideal because according to this guideline, that only improves the structural integrity of that joint, but that doesn't increase the strength. But as I showed earlier, that the capacity performance point of first floor is below the demand curve. So we also need to increase the strength. So we have to consider some retrofitting technique that actually increases the strength of the building along with the structural integrity. So for first floor X direction, as I just explained this part, so we will not do any wing wall installation to improve that joint part. So other retrofitting techniques explained in PWD guidelines or SATREPS-TSUIB guidelines can be used in this particular case. To show an example of one of the new method proposed under this guideline, explained by Sensen earlier in section 3.3, we will use ferrocement retrofitted masonry infill wall as a retrofitting technique for this particular building for first floor. So first we determine how much is our deficiency for retrofitting, that is delta IS, found by like this. And now we want to convert this delta IS or size capacity demand to a lateral load demand. So E can be found by this equation, and IS is found by this equation, as I just explained a little bit earlier. And this is actually explained in the previous manual, seismic evaluation manual. So I'm just inputting this value here and rearranging some stuff, which gives this equation, C multiplies by F equals to this and this. And then C is found by this equation according to PWD guidelines. So I'm inputting this value in this part and doing some rearranging. So you can get the required Q. The Q is actually lateral load carrying capacity or lateral load resistance. So required lateral load resistance is actually the difference of IS0, which is this part, and IS, which is this part. So this one, like, it's a simple value, simple formula, and you can get it. But how do you get what is the existing capacity of that? To do that, you select the floor multiplication factor, obviously, and you have a C value or strength index value for that particular floor at the performance point. Then you have to consider the F value, which is basically the deformation index that you select. So what you select as this is the target of your retrofitted after post retrofitting deformation limit. So how do you select that? It's based on the deformation limits allowed by the retrofitting techniques. Each of the retrofitting technique will give you a maximum allowable F limit. For example, wing wall strengthening might give you a limit of 2.0. For this particular one, as Senshan showed earlier, there are three limits: 1.75 for two types of failure, 1.27 for one type of failure, and 1.0 for column punching. So our case, we are not installing a wing, we are not installing a masonry infill so strong enough that it will produce column punching. So we are considering 1.27, and that's how we determine the existing performance. And inputting values in this equation for first floor, this becomes just 1. So you can simply ignore that, input the values here. And as you can find, we need to provide another additional 191.11 kilonewton lateral load carrying capacity in the X direction. If we can do that, then we can declare this building safe. So as I explained earlier, we wanted to represent focus one of the retrofitting techniques shown or introduced in this guideline. We selected ferrocement retrofitted masonry infill wall as a retrofitting technique, and we selected 4 locations where we actually installed this ferrocement retrofitted infill walls. Previously, there was no such kind of wall in here. We completely installed this and make this frame a retrofitted frame. So why did we select 4? To keep the balance and symmetry in the structure, we selected 4. And how many you need to select based comes on the trial and error process, because you have to select one and get the capacity of one, and then you can determine, okay, you need that many to retrofit this building. So for this case, after doing the trial and error method, we found that 2 is enough to provide the required lateral load carrying capacity. However, we couldn't find 2 spots to retrofit where it will keep a balance in that direction. Because this is the staircase, we cannot retrofit this part, because if we install a wall here, the stair will be completely useless. So this 2 frame is not an option. So that's why we needed to install 4 to keep the structural balance, and it will do some additional retrofitting to the structure, which might not be required. So this is the frame that we considered. Basically, this is IFW1 infill wall, this one, and this has 2 perimeter columns, B2 and B3. So this is the parameters of that. Frame span is this much, and the frame height is this much. And the contact area that was calculated was this much. And using Pythagoras theorem, you can just find the diagonal, which is this much. And as explained by Dr. Sen earlier, how to determine each of the failure modes of this kind of retrofitting. Inclination angle was found by basic trigonometry. And Q frame, there is the existing frame before retrofitting with a masonry infill wall, which is the capacity of column B2 and capacity of column B3, left and right column before retrofitting is found to be like this. Lambda mass is actually found by basic properties of material like elastic modulus, thickness of masonry, number of layers, and moment of inertia of column. Such kind of basic parameters, you get this. Divide pi with 4 times this, you can get the contact area AC as shown earlier. And these are some parameters which will be required for determining the capacity of one of the 4 probable failure methods of this mechanism. So diagonal compression was found to be 936, as explained by Dr. Sensen before with the formulas. And then diagonal cracking was found to be 748 with these equations, and everything is here. Actually shown in more detail in the manual. And overall flexure is capacity is this much. As you can see, it's much higher than diagonal cracking. And column punching and failure, this is also much higher than the other 2 methods. So comparing all 3, as you can see here, lateral capacity of diagonal compression 936, diagonal cracking 748, overall flexure like almost 2 times or 2.5 times higher than the lowest one, 1821, and column punching is 1273. So the minimum of them will govern, in this case, diagonal cracking. And as described in section 3.3 of this guideline, the deformation limit of this was 1.27. And we also assumed the minimum as 1.27. If one of these 2 were the failure mode, say, then we could have gone up to 1.75 and we could have actually extended it. So this can also be a trial and error method based on if you have multiple say deformation limit requirements of the retrofitting technique. After retrofitting, if you calculate and find that your retrofitted wall fails in defined mode and other capacitors are higher, you might be able to increase that range. But on the first trial, it's better to assume the worst case, which is 1.27, because our case, we are not retrofitting enough that this will go to 1 column punching. So we ignored that one. Anyways, this is a trial and error process. So if you make a mistake and find something else happen, just go to the process and recalculate it. So this is the performance of the retrofitted frame, each of them, IFW1 to IFW4. These are the frame strength that was calculated, failure type, story weight supported, and strength index is basically divide this by this, and you can find this. And ductility index limit is actually given by the retrofitting technique on section 3.3 of this particular guideline. So this is the performance of the building of first floor before retrofitting. And note here, we are still considering up to 2.2, not the full range of 3.2 as given by PWD manuals, because this particular building ticked off certain criteria which puts it under a possibility of exerting pull-out failure. And we didn't do any retrofitting to prevent that. So we cannot take the capacity beyond 2.2. So we are still limiting the capacity up to 2.2. Before retrofit, it was like this. And after retrofitting with 4 ferrocement masonry infill wall, at 1.27, the point bumped up the demand curve. And as you can see, now we can declare this particular floor in this particular direction as safe for this. And for the summary, before it was 0.311, and after strengthening it is 0.457. As you can see, it's much higher than the required 0.360, and the judgment can be taken as okay. So that's a brief idea of how to apply this and the previous retrofitting guideline, previous guidelines under this project, and how that can be used to determine the performance and upgrade the capacity of some of the existing buildings in Bangladesh. Thank you.